Please welcome to the biomedical imaging and brain-computer interface session. I welcome our first speaker, Kundu Souraja, and she will present her work called Cross-modality medical image registration with local global spatial correlation.
Hello, good afternoon everyone. I am Souraja Kundu from Kolkata, India, and I am an undergraduate student at Indian Institute of Technology, Guwahati, and today I am going to present my paper, Cross-modality medical image registration using local global feature correlation. So, the problem we are focusing on is to register images from two different medical imaging modalities. We can do with any two different modalities, but our work is focusing on CT and MRI images. So in our data set, we have CT and MRI paired images of the same patient and of the abdominal region, and these images can contain lymph nodes. That is, we have to retain the crucial features like lymph nodes while doing the registration. So registration is a very prerequisite for any kind of multimodality image processing tasks, like if we want to do some multimodality segmentation or annotation by leveraging cross-modal supervision, then we have to do this multimodality image registration as our first pre-processing step. And we can also use it for lymph node classification tasks, since these images contain lymph nodes properly. And I have to first define what is image registration. Registration is nothing but alignment, aligning one modality image with the other modality. And image registration will actually find an optimal deformation field to align one modality image to the other. So for image registration, I will be using a translation-based registration algorithm. So this translation-based registration algorithm has been used in multiple papers, and my innovation is mostly around changing the model architectures and loss functions. So first I'll go through briefly how this translation-based registration algorithm works. So first we have the two images. One is the source image or the fixed image, and another is the target image or the moving image. So we have to deform the source modality image to the target modality image. So here I will be deforming the MRI image according to the CT image. So first I have one pair of real CT and real MRI image, and I will be feeding both of them to the registration network. This registration network will try to learn a deformation field which will contain the information of the CT image, so that the MRI image can be deformed according to the CT. And this registration network will produce this deformation field. This is containing the information of how to move each of the pixels through translation, rotation, or scaling, so that the MRI image now is aligned to the CT image. And to improve the precision of this deformation field, we are employing different translation steps. So the first thing is a cross-modality translation network here. So the first CT image is fed to this cross-modality translation network to generate a synthetic MRI from the CT. And in the next step, this synthetic MRI from the CT is warped using this deformation field, which is being learned from this registration network, producing this deformed MRI from CT image. So this is a two-step registration process, because I assume that initially this deformation field will not be very well learned to do the registration task properly. So we are also backing up this process by translation, because we can also consider translation to be a registration step as well. And once this deformed MRI from CT is created, we now want our deformation field to learn both the local features as well as the global features of the MRI. So for that, to learn first the global features or the textural details, let's say the organs or anatomies, we will first use a monomodality translation network to convert the MRI image to another low resolution synthetic MRI, which I am calling here synthetic MRI from the MRI. And this will be low resolution, so it will not contain the local crucial details, but it will contain the global anatomical structure of the original MRI image. And so I will be using a structural loss function so that this deformed MRI from CT follows the textural details of the global features from the real MRI image. But we have to also incorporate the crucial local details, that is the precision. So that's why I'm employing this precision loss function between this deformed MRI from CT and this real MRI image. And through these loss functions, this deformation field will be learning more accurately. And after that, we will feed this real MRI image and warp it with this deformation field to produce this final deformed MRI. And as also we need to preserve the lymph node level details. So we are using a super resolution loss function, which I proposed in this paper, as well as a patch-wise noise contrastive estimation loss or patch NCE loss. This patch NCE loss basically finds the similarity patch-wise between the real MRI and the deformed MRI. And with these loss functions, we will finally get the deformed MRI. And also I want to mention that these translation networks, I have used the StyleGAN2 generator, and these are discriminator free GAN. So we have a 6-block StyleGAN2 symmetric encoder and decoder network, and the loss function for these translation networks are patch NCE loss and the adversarial loss or GAN loss. And also during the registration, we have to put in some constraint. So I want to mention that registration network will not produce a unique deformation field. It can be a one-to-many mapping. So it is an imposed inverse problem. Sometimes different kind of deformation fields are optimal. So we have to put in some constraints. And here another constraint is the smoothing loss function, which will take care of that there is not very sudden changes in the deformed MRI. So this is an illustration of how the deformation looks like. Let's say we have an image and we get the deformation field, and we warp the deformation field with the image, and the registration is performed. So initially we have a deformation field which has no information in it. It is just a simple straight grid. It has not learned the local transformation parameters, that is how much to rotate, scale, or translate. So this, if I sample the original image with this kind of straight simple grid with a spatial transformer network which is used for warping, then there will be no change. But in the second row, we can see that if the deformation field has already learned how much to transform each of the pixels, and we warp that deformation field with the image, then we can get the registered image. And I have also placed the reference image beside, and we can compare that it has been registered quite well perceptually, as well as if someone can notice that there is a lymph node green colored, which is also aligned properly. So I have proposed the registration network to include local feature extraction block, global feature extraction, as well as local global feature correlation module. So we will first feed the CT and MRI image concatenated into this registration network. And first, this local feature extractor will extract all the necessary details. Then this module is the CNN-based part of different resolutions, just like the encoder part of a unit. And then we have a global feature extractor. So this block will act on the local feature details which has been extracted. So these local features which have been extracted are now combined to get an overall global estimation or some global features like the anatomies or bone regions, the textures, etc. And this global feature extractor block is BGRU based, bidirectional gated recurrent unit based. And finally, we now have the local and global features. So we will have to correlate the positional information. That is, we have to place the small crucial local details at proper places or position in the global features so that the registration is perceptually perfect. So for that correlation task, I have used a visual transformer, and after that we will apply the feature reconstruction, which is also like the decoder part of a CNN-based unit architecture. And finally, the output of this registration module will be the deformation field. The model architecture looks like this. As I mentioned, that the first part is a local feature extraction block. So this really looks like the encoder part of unit with the 3x3 convolution and leaky layers. And then we will just rearrange the feature tensor to make the size compatible, and then we will feed it to the global feature extractor block. So the first item here is the BGRU layer. And then there is a transcon layer, a ReLU, and a squash attention layer. So this part will capture all the global features. Then we will first tokenize this, and I have used a recurrent tokenizer, that is to improve the speed of tokenization. So in this recurrent tokenizer, at each layer, the tokenization process depends upon a weight vector which controls the influence of tokenization from the previous layer. So after this tokenization, we will get the tokens as different visual concepts. These concepts can be both local concepts and global concepts, like the bone region, the texture details. And after that, this positional embedding layer and the dropout layer will prepare the final embeddings, which can be fed to the transformer for local and global feature correlation. And finally, there is this visual transformer, and after that I'm just reshaping it, and then just reconstructing the features through some transcon layers, and then again leaky ReLU and con layers, transcon layers. So these stacks are going on just like a unit architecture, and there is skip connections from the encoder. So the loss functions which I have used in this architecture, the precision preservation loss is just nothing but an L2 loss function. The structural loss is also L2 loss. And finally, we are using this patch-wise noise contrastive estimation loss. So it will first extract image embeddings from each image patch. And to extract the image embeddings, I have been also using a feature network. And this feature network contains some MLP layers as well as a GALU activation function, and also self-attention layer. And after that, this patch embeddings will be annotated with positive embedding or negative embedding, and there will be a contrastive learning. So that is how the patch-wise noise contrastive estimation loss works, and this has been used in the baseline model paper called DFMIR, that is the discriminator-free multimodal image registration model. And as the smoothing loss, I have used the L2 norm of the gradients of the deformation field. And finally, the super resolution loss function which I proposed, this is nothing but the L2 norm of super resolved features. So to extract the super resolved features, there is the super resolution CNN model I have used, which is from this paper here. Image super resolution using deep convolutional network. It's just a few CNN layers to extract the super resolved features. So for extracting that, I'm only focusing on the central region of the CT and MRI images, where there is the highest probability of finding a lymph node, and I'm just kind of zooming into that region to get the high resolution details and comparing them with the L2 norm. And finally, for the translation networks, I have the GAN loss, the adversarial loss in image-to-image translation networks. So these are the results of model comparison. So I have the moving image and the fixed image. The moving image will get deformed according to the fixed image. So we can see that the proposed model and also the DFMIR both are giving perceptually very good results. So these are some other comparison models like NEMAR, affine transformation, and NEMAR unit. So affine is just doing the rotation translation or scaling, and it is not really doing the deformable registration. And the unit is doing deformable registration, but we can see that the results are very poor. One reason is that I have trained the model with very small data set because it is in medical imaging. It's very scarce to get paired CT and MRI of the same region of the same patient. So we have to learn working with very small data set, and our model can give good performance even with a very small data set, as small as with just 60 images. And it can, of course, if we increase the training data set, the performance will improve. And so I have done the experiments in 2 datasets. The first dataset is Aichi Cancer Center dataset, and the second dataset is a Sintran Grand Challenge dataset.
Conclude in a few minutes.
Okay, sure. So these are the model comparisons. The results, I can see that the proposed model is giving the best performance in terms of structural similarity index, mean square, and normalized cross correlation coefficient. And also these are the ablation study results, and we can verify it from these statistical parameters, and also we can see that our model is giving the best performance among all the other ablated versions. So the conclusion is we have used some dropout layers and Stallion-2 generator network, which improves the training speed by 36.7% than DFMIR, and it has a very good generalization capability because it can be trained on a very small data set. And these are the statistical improvements over the best performing competitive model DFMIR, and also we have proposed this local global feature correlation to and super resolution loss function to retain the lymph node level details. Thank you.
Thank you for a very good presentation. Questions? I would like to ask a question. Some of the regions in your images are rigid regions, such as bones. Are you treating all pixels equally? Do you think different regions could have different characteristics, rigidity?
Yeah. So you mentioned bone regions, so those will be the global regions, and in some cases there will be very crucial details and so much contrast, high contrast. So for extracting the features, I have to do at different resolutions, basically. And for different resolution, I have the CNN encoder, which extracts the features at multiple scales. So it will take care of both those bone level global details as well as the small crucial details.
Any questions from the audience? Second question is, is there a preliminary course registration step? Does it matter if they are not, is the starting point important?
Okay, so I have not done any pre-processing with rigid registration, so still it performs quite well without any affine transformation.
Please join me in thanking the speaker.
Okay. Thank you.